In the slides that follow, I will briefly summarize the main transformations that take place in the computational loop for perception and synthesis of movement shape. As we can see, the loop initiates with a demonstration shown to ICUP by the teacher. It can be a teacher performing a specific movement like U or whatever, or demonstrating the use of a tool. There is a motion detector system which basically extracts the end effector trajectory of the teacher performing the movement to the robot. So the output of a demonstration is a trajectory or a set of trajectories. To move from trajectory to shape, we basically use the catastrophe theory framework. So the idea behind catastrophe theory is rather simple. All that it says is that shape of a smooth function is determined by a set of special local features which are called as critical points. Let us try to understand this using an example of a simple sketch of Gandhi. This is the side view of Gandhi. Now if you look at it carefully, there are some special events happening all along the trajectory which we would like to extract. For example, there is a smooth bump in the beginning, then it moves to a sharp inflection and once again a smooth maxima sort of a curve. So these are the special events, and global shape is a set of local shape features. In a very nice work way back in 2003, Chakravarti and Kompella proposed a set of just 12 shape features which is sufficient to characterize the shape of any trajectory in general. And they can be formally classified in a very easy way. They are finite because there are just 12 of them. They can be combined to give rise to a diversity of shapes. For example, the shape of Gandhi itself is a combination of interior point, end point, a bump, there is a cusp which is the sharp inflection. So global shape is a composition of local shape features. So once all the critical points in a trajectory are known, you know the shape of that function, or you can move from a Gandhi sketch to a shape of Gandhi, or from a trajectory like U to the shape of U, and so on. So by extracting the shape of a trajectory, we reach a representation which we call as the abstract visual program. Now there are two things which we should note here. Firstly, when a teacher performs a movement, he performs it in his egocentric space. And when ICUB observes the movement of a teacher, basically the trajectory and its shape is computed in the image plane, or it's visually observed. Now first thing we need to do is transform this shape representation into ICUB's own egocentric space, because it is going to perform the movement in its egocentric space. The second thing is that the shape itself is devoid of context. So we need to impose additional context as to what will be the scale of the U I will make, or what is the scale of the circle I will make. Am I going to make it with the left hand or the right hand, or with some tool like a steering wheel held in both hands? So task specific constraints have to be imposed to the shape representation, and secondly, this representation has to be transformed from the image plane to the egocentric space of ICUB where the action will take place. So when these contexts are imposed, to the abstract shape representation, what you get is a concrete motor goal. That is, a concrete motor goal is an abstract shape representation plus all the other task specific details that needs to be taken into account to perform a goal directed movement. So basically we have now moved from the observation of a teacher's demonstration to the creation of a concrete motor goal in ICUP's own egocentric space. In the next slides we will look at how the goal is now achieved, or ICUP learns to replicate the movement itself. So this is where we come to the virtual trajectory synthesis system. What this system does is exactly the opposite of shape extraction system. That is, it converts a shape into a context specific trajectory, or it converts a discrete sequence of shape critical points into a continuous sequence of equilibrium points, which act as an attractor to the specific end effector that is defined in the motor goal. We all know that given a sequence of 3 points in space, an infinite number of trajectories can be drawn passing through them. So the goal of the virtual trajectory synthesis system is to come up with the correct values of parameters such that the shape of the trajectory generated is equivalent to the shape that is described in the abstract visual program, or equivalently concrete motor goal. What we have shown is that by modulating two parameters, it is possible to learn the transformation from shape to trajectory. These two parameters are the virtual stiffness, which is represented by K, and the timing of the time-based generators, or as we see in the slide of the virtual trajectory synthesis system, for one set of values of stiffness and timing you get a bump, and for some other set you get a cusp. So the goal of learning to shape is a problem of learning the right values of virtual stiffness and timing such that the shape of the trajectory generated by ICUP correlates with the shape description in the concrete motor goal. How difficult is it to learn these parameters, considering that they are open, is a question which we should address now. Now we can treat this problem of learning as compared to the optician analogy. When we go to an optician to get our eyesight checked, he babbles with a few set of lens, and with your feedback, within minutes he is able to converge to the right dioptric value of the lens that you should be wearing to get your eyesight proper. Is very similar to that. What we have shown in the paper is that just by babbling from 1 to 10, as you can see, we can generate the basic critical points, which is the line, bump and cusp. There is also a story in the numbers. For example, while you generate a shape like V between 3 points, it involves straight lines and the stiffnesses are 10, 10, 10, 10. If you want to generate a sharp cusp, the values change from 10, 1, 1, 10. If you want to generate a smooth bump, then the values just go the opposite, 1, 10, 10, 1. So it's very easy to learn to generate the basic shape critical points. And once you know to generate line, bump and cusp, you can immediately generate all the other critical points, because these are basically compositions of line, bump and cusp themselves. For example, a contact is a meeting point between two bumps. A peck is a composition of a line and a cusp, and so on. And if you can generate all the 12 critical points, then you can generate the shape of any trajectory in general, be it a S or a line diagram, or even trying to imitate a teacher steering a toy crane. So this is the basic idea. You can learn the basics and then bootstrap the basics to slowly increase your knowledge to move to more composite shapes. And once you learn all the critical points, you can generate any trajectory in general, because you have acquired the grammar to compose anything based on context.